Hi everyone, welcome back to my garage, and welcome back from your week of vacation. Not that it was probably much of a vacation, but it was a week off of schoolwork. So with the announcement that schools are going to be closed for the rest of the year, it looks like this is how we're going to have to do related. So this is our classroom. I would much prefer to be with you guys at Baypath in our regular classroom. I don't really know why, but talking to the camera like this and teaching like this just isn't the same. I miss interacting with you guys. I miss actually having a live audience. This is harder than you realize to do, but I'm doing my best, and hopefully I get a little more comfortable with it as we go. So if you think back to last week, the week before, we were learning about ignition systems. We talked about points and distributors a little bit. We started talking about magnetic pickups and ignition modules a little bit. So we're going to kind of pick up there. And my goal is to talk about the three types of triggering devices we use in automotive ignition systems. To this day, we still use the same basic three, and how they're used, how they operate, what the parts are for each one. There'll be a small assignment to go with this video, and hopefully I get it right the first time, because I have no editing software, so if I mess this up, I have to do it all over again. This is take 3, by the way. So, triggering devices. Okay, so the first triggering device we talked about a little bit last week was the magnetic pickup. It can also be called a pickup coil, or a pulse generator, or even just a pulsar. So different names from different manufacturers, but they all basically do the same thing. I'm not too sure how low I can go on this before I lose it, so I'm going to erase these. I miss my big whiteboard too. So as we learned last time around, this was a device they came up with to replace mechanical points, because points kind of stink and they wear out. So in place of the little cam inside the distributor, there was a little rotor, or a reluctor they call it, and it's going to have some teeth on it. There'll be one tooth for every cylinder of the engine, so if it's a 6-cylinder engine, you're going to have 6 teeth on that reluctor. Near that reluctor, there's going to be a little metal pole. We can make that a little bigger. Call that a pole piece. And they call that a pole piece because it's kind of like a magnetic pole. So attached to that pole piece, there's going to be a permanent magnet. Last but not least, wrapped around that pole piece, you're going to have a coil of wire. Okay, so that coil of wire is going to have 2 ends, so you're going to have 2 wires coming off of this inside the distributor. It looked like this. Let's see if I'm in the shot. So here's my reluctor. This isn't bolted together properly, so it might not spin. Oh, there it goes. There's my reluctor spinning. My thumb is covering the pickup coil, and the magnet is underneath this metal piece right here. So you see there's 2 wires that come off of this. And what happens, if you remember from last week, is this reluctor spins. It disrupts the magnetic field that's coming through this pole piece, and it causes the magnetic lines of flux to kind of move through that coil. And as those lines of flux move through this coil, they induce or create a small AC voltage. So this is going to make an AC voltage. And that AC voltage is what we're going to use to trigger our ignition control module. So this guy right here. So our ignition control module. This little transistor right here needs to be told when to turn on and off so that it can fire our ignition coil. It needs to make and break the magnetic field inside this ignition coil, so we make and break the circuit. So that transistor gets signaled by that magnetic pickup. So that's one way to accomplish a triggering device or a pickup to trigger the ignition module. And that's still in use today. Now that we don't have distributors anymore, we have to kind of get creative how we do this. So this magnetic pickup right here, you can see it's maybe a little bit smaller than the one inside the distributor, but it's got kind of this long extension. This pushes into the engine, and this is actually going to kind of butt up against either the camshaft or the crankshaft. And they're going to basically machine a spot in the cam or the crank to become the reluctor. So the teeth can be very small. Basically, we can cut those right down. Basically turn them into nothing more than just little bumps, little machine surfaces. And this sensor can just push in through a hole in the block, and it's encased in plastic. It's impervious to oil, grease. It's pretty temperature resistant, and it's a simple, reliable little trigger device. So really not much in there. There's a magnet. You can see it's magnetic. There's a coil of wire, and there's two little terminals, which you might be able to see, you might not, right in there. And this is going to work the exact same way as it did 40, 50 years ago in distributors. Alright, so that should be our little refresher on a magnetic pickup. As far as the pieces, you need a reluctor, the pickup coil itself, which is your pole piece, and your permanent magnet. This is all kind of one component, and that's the pickup itself. So the permanent magnet creates a magnetic field. The pole piece sort of directs that magnetic field over by the reluctor, and then there's a coil inside there, and it produces AC voltage. So, yeah, the one thing I didn't label, the coil. Little coil winding. Alright, so that wraps up a magnetic pickup. One reason you might not want to use this is this AC voltage that it produces. Some manufacturers prefer not to use this because an AC voltage is an analog signal. It doesn't have a crisp on and off quality to it like a digital signal does. So a digital signal is on or off only. It's all or nothing. It's 1 or 0. Whereas this AC voltage sort of fluctuates. So this makes more work for the ignition module or the computer in a modern car, because they have to convert this signal to a digital signal before they can do anything with it. So some manufacturers prefer to use a different triggering device. The two that we're going to talk about today are known as Hall effect sensors and optical sensors. Okay, so we'll start with the Hall effect sensor. So this is a digital triggering device. This is going to produce an on-off signal, so it's a little bit more precise, it's a little more accurate than a magnetic pickup. They're pretty reliable. They can go into a lot of different places, kind of like magnetic pickups. They can be placed down behind the crankshaft balancer. They can be inside a distributor on an older vehicle. I've got a distributor here that has a Hall effect in there. I'll give you a close-up on that in just a minute. And basically, there's still going to be a moving piece, although in this case, it's not going to be a reluctor. Alright, so there's going to be a round ring inside there, and that ring's going to have some openings in it. And there'll be as many openings as you have cylinders if it's in a distributor. So if it's a 4-cylinder, there's going to be 4 openings, and what that leaves behind is 4 little metal blades or shutters. If it's a 6-cylinder, there's going to be 6 of these. If it's an 8-cylinder, there's going to be 8 of them. They'll probably be a little more uniform in size than what I drew right there. And what these are going to be doing is they're going to shield a magnet from this Hall effect sensor. So on one side, there's going to be this little sensor, and inside here, is a tiny little semiconductor chip. Over here, there's going to be a little magnet. So we have a magnet in here. We have a little ring of blades or shutters. We have this Hall effect chip right here. And there's going to be some electronics in here. And there's usually going to be at least 3 wires coming out of here. So one of these wires needs power to make these electronics work. If you were guessing a ground, you'd be right. And the third wire is going to be our signal. And that signal is going to go to our ignition module or to our computer. And the neat thing is it's going to be digital. Which basically means it's like 1 or 0. It's either on or it's off. And that's going to be much more precise than the signal that comes out of a magnetic sensor. Hopefully I can fit it down here. On a magnetic sensor, you get an AC signal, and as we learned during alternators, AC makes a sine wave. It makes this kind of curvy, lumpy wave, and that's what we call an analog signal. Whereas this Hall effect is going to make a square wave, or what we call a digital signal. And this is going to work better for our ignition modules. This is going to work better for our computer. I'm going to peek over here and see. Yep, that does show up on the camera. Good. All right. So how this thing actually works, this little semiconductor chip basically generates a tiny, tiny voltage when it's aligned with this magnet. As these blades and shutters rotate, because these would be either down inside the distributor or attached to the back of the crankshaft pulley or wherever the manufacturer chose to put it, as they rotate, they alternately expose the magnet or block the magnet. They shield it. So these would be like steel shutters. They're going to shield that magnetic field. So that's going to cause this chip to produce little voltages. The electronics in this sensor are going to use those little voltages to produce this nice digital on-off signal. So every time the magnet is exposed, we get an on. Every time the magnet is blocked by one of those vanes, we get an off, etc. So as this spins, these little on-off pulses get produced, and we use that to trigger our ignition. So I'll give you a close-up of one of these. So this is an older Ford distributor. This gold piece right here that spins, those are the blades or the shutters, and I'm going to take those right out of there so you can see them. That better view. Just like the cooking shows where they prepare everything ahead of time, I loosen these screws ahead of time. Okay, so that's going to come up out of there. So you notice this thing has 1, 2, 3, 4, 5, 6 blades, because this was a 6-cylinder. And Ford was nice enough to stamp 6 in there just for the people on the assembly line in case they couldn't count. So we look down inside here. Make sure I can get this in the shot. All right. Turn that. Oh, look at that. So this little triangular piece right there, that's the magnet. And then the Hall chip itself, the Hall element, is inside this little black plastic piece. It's very tiny. So those blades either block the magnet or expose the magnet. Block, expose. Okay, so Ford, just for some history here, went through a couple different designs. You notice this one's just got a flat metal spot here where I wrote Hall effect on it. And this one's got this little black box. So this distributor is a slightly older one. This black box is the ignition module. So rather than this firewall mounted or fender mounted ignition module, they chose to put it right on the distributor. And they learned through experience that this wasn't a great place to put the ignition module. It gets overheated and it fails. It kind of fails prematurely. So the This is one of those Ford ignition modules that failed, and somebody peeled the cover off so you can see inside. This was one of the first automotive uses of this really tiny printed circuitry. This stuff is really common now in home electronics, computers, TVs, stuff like that. But this tiny surface mount electronic circuitry was kind of revolutionary at the time. They called this a Tfi module, which stood for thin film integrated, and this was the film. It was this little thin film-like circuit board, and these things would overheat and stop working, and then the car wouldn't run. So on the later years, Ford closed off the distributor bowl where it used to mount, and then wires came out, and they put this module over on the fender. So they kind of went back to a remote module. Worked a little bit better. So because these, well, I'll stand in front of the camera, I guess. Because these sensors came about a bit later, and by the time they started using these, we had computer-controlled engines. We weren't just looking for an on-off signal for the coil. We wanted a little more than that. So you might notice one of these blades is narrower. And I don't know if they did it to the leading edge or the trailing edge, but maybe I can tell by looking at it. I can't really tell. I think this edge is the same, so I think this is the different one. But again, I could be wrong. Maybe we could tell by looking at the gaps. This is a wider gap, so I'm going to guess this edge is the one they trimmed off. At any rate, the signal that would come from this thing as it's spinning would have one non-uniform little square wave, and the computer would use that to figure out where top dead center on the number one cylinder was. So that wave would kind of look like this. 1, 2, 1, 2, 3, 4, 5. And I ran out of space on my board, but you get kind of the idea. One of those little square waves is a different size. So we could still trigger the ignition coil every time we needed to. If we use the leading edge, and I don't know if Ford used the leading edge or the trailing edge, I really don't know, but it doesn't really much matter for this discussion. We could still trigger our ignition coil every time we needed to, but then the computer could detect that corner was different than this one, and this one, and this one, etc. So it knew which one of those teeth represented number one cylinder. So that was important for fuel injection, so we could open the fuel injectors at the right time and spray fuel in the right cylinder at the right time. The ignition system didn't care about that, but the fuel system did. So, and by the way, you can do something similar with a magnetic sensor. You have to have an uneven number of teeth on your reluctor, and that's something that we do nowadays as well, but the examples I have here are too old for that. So on this old magnetic sensor, all 8 teeth here are the same. If we had like a 9th tooth somewhere or a missing tooth somewhere, then the computer could do the same thing. It could figure out where number 1 is. Alright, so hopefully I don't sound too monotone or I don't know, unnatural talking to you like this. I feel pretty unnatural talking to you like this, but I'm sure I am. So, one more thing on the Hall effect before we move away from it. Different manufacturers did it differently. This was Chrysler's method. When they had distributors, this just sat down in the distributor right underneath the rotor, and there was a little trigger wheel, so they made it a little easier to change, which was a good thing because it did fail. This one, I think, was off of an old 2.2 or 2.5 Chrysler, and you can get kind of a better view. So there's the magnet. The Hall chip is in here. On the back, this little plastic shield actually pops off. You can actually see the 3 tiny little wires going up into the plastic, and that's it. This little sensor, it's cheap, it's reliable, it gives us a nice digital signal, so nice technology. Okay. My board's still in focus, my camera's still recording, so that's good. I know at one point this thing stopped recording on me, so doing good so far. That's your Hall effect sensor. So you've got a magnet, you've got blades and or shutters, and you've got a little Hall effect chip, a little semiconductor chip. Okay. The last triggering device I want to talk to you about is maybe a little less common than the other two. It's actually one of the best, and that is the optical, also known as photoelectric sensor. Okay, so if you think optical or photo, both of those things have to do with light. So this is a sensor that works on light. Basically what they do is, instead of a reluctor or a rotor inside a distributor or on the back of a crankshaft pulley or in the crankcase. Matter of fact, this can't go inside the crankcase, as you'll see in a minute. You'll find out why. This has to go in someplace clean and dry, which a crankcase is not. Wherever they put this sensor, they're going to put a little disc with slots punched in it. And that disc is going to rotate. I don't know why I'm drawing that so small. I've got space. So we have a disc that's going to spin. We're going to punch some holes in this disc. On one side of the disc, we're going to put an LED, and I know you guys know what an LED is. We're going to give this power. We're going to ground it. And that little LED, or light emitting diode, is that key, light emitting diode, is going to shine its light at this disc, and in reality it's going to be aligned very closely and very accurately with this disc. On the other side of the disc, there's going to be something that's similar to an LED, but it's not. It's something called a photodiode. So again, we have optical, we have photoelectric, we have a light emitting diode, we have a photodiode. So if you haven't guessed yet, a photodiode is a diode that responds to light instead of making light. So when the light shines through one of the holes, of course I didn't do very well. I can draw however I want. I'm making more holes. How do you like that? There we go. When the light shines through a slot, so that the light can come out the other side and strike this photodiode, that photodiode is going to turn on and it's going to produce a tiny current. That tiny current can then be amplified by some electronics and turned into a signal. So if you can see where I'm going with this, as this disc rotates, sometimes a slot is going to align and the light's going to pass through. Sometimes a slot is not going to align and the light's not going to pass through. So this photodiode is going to basically be constantly turning on and off and on and off and on and off and on and off, etc. That's going to give us another nice digital signal. On and off. And I actually made a trip to the school the other day to bring home some parts and pieces. This Hall effect distributor that I brought home came from the school, and I have a nice optical distributor at the school, and I couldn't find it. I wasn't in there very long. I kind of needed to make it a hit and run, get in and get out, and so I grabbed as much as I could. I grabbed some stuff to do some other lessons, and I tried to find my optical distributor, but I don't know where it is. So since I couldn't find it, I had to kind of make a representation of one. So I took this little piece of cardstock here. Does that show up in the... Yep, you can see that. And I punched some holes in it. So I'm going to stick my pencil in here. So this would be how the disc would be spinning inside the distributor or inside the housing where this sensor lives. I should mention this thing has to live in kind of an enclosed, sealed, clean environment. This isn't something that's going to work too well outside, exposed. You can imagine that if dirt or crud got on the disc, the little slots, the little holes would get blocked up, and then you're not going to get a reliable signal. So just to give you an indication of how this works, let's see if I can make this happen. As it spins, see, is that coming through? Yep. I think it's freaking my camera out, but it seems to be working. And I think I probably should have made this disc out of some darker color material, but I think you can see that when the slots go by, the light shines through. And that would be triggering the sensor. So I do have this little optical sensor. This is an old optical sensor that was sold as part of a conversion kit, an electronic ignition conversion kit. And this was something you would put down inside the distributor where the points used to go, and they would give you a little disc that would slip on underneath the rotor, and then you'd have to wire this up to an ignition module. And I'm going to do my best to show you. Hopefully you can see. If you look right by my thumb, right in there, you can sort of see the little clear lens of the LED. And actually, I don't know if that's the LED or the photodiode. They look the same. And up on top is the other one, up in there. So that could be the LED up top, and that could be the photodiode down there, or vice versa. I don't know, but it doesn't much really matter. And what you might notice is that it kind of has that clear plastic look, kind of like the LEDs you see in the end of remote controls. It's the same type of LED. So this type of LED makes light, but you can't see the light. This is going to be infrared light. If you have a fancy camera, you might be able to pick it up. My cell phone camera does. I highly encourage you, when you're done watching this video, go grab the remote control to whatever you have in the house and point it at your cell phone camera and see if it can pick it up. Some can, some can't. So if you look really close there, you'll see a flash. There it is, a little flicker. So I've noticed most iPhones can't pick it